Lecture G7 Acoustics. This one is about sound and noise. It's talking about sound insulation against external noises, and acoustics in the urban space design. Sound basics. We are aware of sound. It either comes by traffic or aircraft, or it comes by building service systems, or us as people delivering noises. Traffic noise, mainly traffic noise, truck, airplane, train, tram, other vehicles, which is 3/4 of the impact, and 1/4 of the impact is what we as people do. Restaurant, leisure, neighbors, that's the main resource, and construction site, obviously, if they happen. We do divide airborne sound versus structure-borne sound. Airborne sound means there's a sound device which creates me, for example, with my voice, creates a certain airborne sound, which is then hitting surfaces and then maybe transported, or structure-borne sound when I knock the wall, clock, or like in this picture, the hammer knocks the wall. We do deal, or we measure this by frequency. Sound has to be understood as, say, energy impact to the air, and then creates kind of movement in the air. That's measured in frequencies. To 1 Hertz to 100,000 Hertz. The building acoustics we deal with is 100 Hertz to 3,150 Hertz, so quite limited range. The language is a bit more. It's 100 Hertz to 8,000 Hertz, and the human hearing, that's from, if you're not that old as me, 16 Hertz till, what is it, 20,000 Hertz. So in the building acoustics, we deal with a lot lower range, a lot smaller range than what we actually are able to hear as frequency. We measure this in decibel. The quiet living room, for example, the 50 Hertz sustainable suburban residential neighborhood, 50 Hertz, the 60 Hertz in normal conversation in 1 to 2 meter distances, and then you see all the heavy truck, the jackhammer, the rock band 110, and the airplane with 120 decibel. And we need to consider that this on say unlimited or an ideal boundary condition, no shielding, no reflection, no absorption, the sound emits from its point of source in a spherical way, which means we have that energy impact to the air, and then it actually reduces enormously by spreading out. It actually reduces by the number of 6 by doubling each distance. So we have the 90 dB, and then it's 6, it's 84 dB, and then doubling this distance, it's 70, 80 dB. So it reduces intensively or largely by the logarithmic level. The sound impact, 75 decibel, and then the certain distance, reducing it by 6 as a number. The noise transmission happens via this impact to the surface, and the surface starts to move, and then obviously also transports this energy to the other side, and then starts to move the air there, and that's what we hear as sound. And this transmitting can happen in both ways, from outside to the inside as well as from the inside to the outside. Depending on the type of structure, we here use the typical setting of the structure, so the solid structure, single shell solid structure, where the mass itself actually reduces this impact versus, for example, lighter structures like this ventilated facade, where we have an outer layer, super light insulation, and then an inner layer, a bit less than the solid structure there, which then moves in a different setting, and I'm going to see that in a slide, may also starts to combine as setting. Sound insulation against external noises. What we mainly have to do with facades. So we need to identify where comes the source, top picture, where comes the source, how does it influence our facade, and then how is it transported to the inside, versus the other one, where comes the source and how is it reflected to our inside as a setting. We need to, this is frequency, the line of frequency, and the sound reduction index R, so the resistance against sound reduction. And we see on the pretty left side, it's plate vibration, so solid vibration. Then the law of mass. The mass itself starts to move by the sound impact, getting an impact and then delivering the impact. Then there's this effect of the mass starts to vibrate, and depending on a certain frequency. The frequency is actually to be defined by the material itself. And then again, we come to this law of mass. This is for a single structure. So there's a certain point where a single structure, depending on the impact, for example, very low frequencies of solid structures, starts to move, and by that transports the sound to the inside. When we combine this to two shell structures, we may find a difference. So we see again the pretty much far left, the mass itself. Then it significantly increases, so the performance of the mass, performance of the structure increases. So you have two layers, and these two layers are actually moving in different levels, especially if they're having different weights. Then it gets even better, and at a certain point they start to move both in the same way, and then it actually decreases. So in principle, double-layered systems are more efficient than single-layers system, as long as you say define it with the law of mass and the certain masses of the material as setting. This whole thing results in the resulting weight airborne sound insulation value in decibel, which is defined by the single area of the various components, the total area of the various components, the weighted airborne sound insulation value of individual components in decibel, and then the numbers of components. So actually this resistance against the sound of a structure depends pretty much on the different components of the structure and the size of these components in relation to the global size of this. How do we deal with that? A sample next to just solid structures, a sample are, for example, these double facades, which are actually having an inner and an outer layer, different weights, and this outer layer actually protects from the first airborne impact of sound to our structure, and then hopefully this inner cavity allows to, for example, ventilate a bit. If we need to do other penetration of structures, we may deal with this kind of devices, having the solid facade still needing ventilation for our structure. We may end up with these sound absorbing devices, which then in a certain way allow the air to flow through, but still protect the sound impact to these devices. Last words about acoustic urban space design or acoustic in urban space. We are till now only preventing the inside from impact of sound to the outside, but we have to be aware of that urban spaces are intensively getting acoustic impact. There's this noise mapping, which you can, for example, get for the German environment entirely for each place to identify how much noise you get. And this noise ends up in a noise source, which we see on the left side, noise source from the outside, which directly hits the person and gets reflection from the facade to the person, which may end up in a doubling or an additional sound impact. We may reduce that by having a sound absorbing facade and sound absorbing outer surface facade. There's research done, which Jochen Grimm, for example, did a nice PhD in Delft about this. He investigated very sound reflecting surfaces and identified that this noise accumulation could be in the end actually harming by stress. And this could be reduced by, for example, adding sound absorbing surfaces, which then reduce reflection to the person as a person, so they only get the direct sound and not the total sound, which is a way of reducing the sound impact to a certain urban area, if interested. This whole thing obviously can be found in this building physics book, which we did about facades, and the building physics lectures, which we do in Darmstadt. And as usual, this is a Delft Darmstadt Munich facade education project with the number of people participating in sharing their knowledge. And by this, I stop.